So I wanted to talk today about linear mixed and generalized linear mixed models. Now I have to confess that this is hard material. Okay, so mixed is quite a short word in English, but it's, I'm afraid, quite a complicated word when it comes to mathematics and statistics. Okay, so this is hard material, but I wanted to provide you with as realistic data examples as possible, and these problems that I'm going to discuss in this lecture actually came from a genuine industrial problem. Okay, so it's a practical subject matter, and it's also a practically sized data set. Okay, and I think one of the things that comes as an offshoot of that is that you needed a high-level programming language like R in order to process some of this data. Okay, this would have been an ordeal to have to do by hand using the menus using Excel. So, like I said, what we've got here is a practical industrial problem and a professional standard solution using these two things here, linear mixed models and generalized linear mixed models, and some of the manipulation of the data set using R was also significant, indicating, I think, that for real problems you're probably going to need a high-level computer language, even if you could get away without that for your dissertation. The outline of the lecture today then, so I wanted to go through these two industrial problems and then talk about the simplified analysis of problem 1 using regression, and then simplified solution of problem 2 using generalized linear models. So in these two solutions here, a repetition of what you've seen before. Then I wanted to say a little bit about generalized linear mixed models. Now, trust me on this, mixed is quite a small word in the English language, but it's quite a complicated word in statistics. And then I wanted to give you, in contrast to sections 2 to 3, firstly, a proper professional standard solution of problem 1 using linear mixed models, and then a proper professional standard solution of problem 2 using generalized linear mixed models. Okay, so I did want to give some repetition of what you've seen before in sections 2 to 3. Here, it's, I think, for the first time that you're using these models. They give you plausible answers, okay, but you actually need the mixed models in order to give you the true full solution. So there is actually quite a dangerous thing here, that you're using proper statistical techniques to give you plausible answers in sections 2 to 3, but it's actually too simple an answer unless you use the mixed models in sections 5 to 6. So it does emphasize here, I think, that statistics can get hard when you've got a real problem and a real data set. It's not obvious that you can solve these things when you first see them. So the first problem is a big data problem, and again this comes from a genuine industrial problem. So in regional monopolies such as electricity and water industries in the UK, customer satisfaction scores form the basis of regulatory fines. Now, the whole system is potentially unfair if there's a detectable regional bias, i.e. a regional effect over and above the actual level of service received. And I wanted to here try and measure regional bias using data from TripAdvisor. And again, this is a practical industrial problem. It's not necessarily obvious a priori that there's a solution here. So the data recorded are the hotel, the rate and the rating out of 5, the higher the better. And in this lecture, I'm going to treat the data first of all as if they are a continuous numerical variable. So this is a subtle point here. It may not actually be strictly mathematically correct, but it makes it easier to use and interpret the model. And it does show you here that what we've got is a industrial problem, and there is no substitute for common sense. So important aspects of the subject are not just purely mathematical. They do rely on a bit of interpretation, communication, and common sense, though they are probably inherently quantitative. Okay, so I would argue that any training you receive in econometrics, mathematics, and statistics not wasted. Okay, but here we've got a practical industrial problem where you needed an element of interpretation and common sense alongside that. So in terms of problem 2 then, so we've got the same data set of scores, take the values 1 to 5, and we're going to categorize these as high scores being 4 to 5, medium scores of 3 out of 5, and low scores of 1 to 2 out of 5. And in this lecture, what we want to do is try and investigate how the probability a survey respondent gives a high score, a medium score, or low score, depends on the region of the survey respondents. Okay, so what you can hopefully sort of see if you squint a bit, this does relate to some of the material that we covered in the last lecture. Okay, but again, this is a practical industrial problem. Okay, it came from a problem in the electricity industry, and what I wanted to emphasize here is that this was a practical problem. It's not necessarily clear a priori how to do this. Okay, so as I said before, we'll go through two solutions. So the first solution using either linear regression or probability regression models, and then the second professional standard solution using mixed models to account for some of the correlation structure in the data. And what we will see is that you need these mixed models to account for the correlation structure in the data in order to get the analysis correct. An overly simple model for regional bias in these customer satisfaction scores. This is going to use the classical linear regression model. These are actually dummy variable regression models because the X variable here, region, is a group of different categories rather than a set of different measurements. So the basic problem is there evidence of regional bias in this data set? So we start off with this regression model here. So the score is going to be equal to some constant term plus a beta value times the regional term, and there are a number of subtleties here. So for the moment we ignore the effect of different hotels. So if you put the effect of different hotels in, you have mixed models. So in practice this is actually quite a dangerous data example because you get quite plausible suggested answers to the problem at hand with the slightly wrong model. The idea would be that if you express the model for score in this regression equation, if the beta terms in the regression are significant, then you have evidence of a regional effect. And then the beta terms would help you to quantify the practical effect of any regional bias. And this is important because these customer satisfaction ratings form the basis of the fines that the regulator can impose. So in terms of regression modelling in R, so lots of things here that you'll have seen before. So I always say think R for robot, and usually you have the same rhyme and rhythm every time you fit models in R. So you run the analysis. For regression it's a linear model, so the command is lm to reflect that, and then display the results, and there's a separate summary command to actually show you the results of the computations. R is like a robot, it won't actually show you the results unless you use this second command, summary. Now the default in R is to fit a constant term. Now this is not explicit in the R syntax. This can be suppressed using a -1 term in the sequence of X variables. Now usually you include a constant term automatically, and what I wanted to give you here was a example where it actually made sense to suppress this constant term. Now it's an unusual example, I wanted to include it here because it is a practical industrial problem. Sometimes I think it's helpful to see that these things aren't necessarily always so uniform. Also, this is a mistake that me and another professional academic made in our paper. We didn't actually come up with the optimal way of displaying the results, so that sometimes these things aren't as nice and easy as you might imagine, and even professionals who are good at the job can make certain communication errors. So in the simplified regression treatment of problem 1 then, so the data is in the file scoredata.xlsx, which gives the ratings of 24,365 reviewers for a range of different products. Products are hotels. Now you could argue whether this really is big data. My view was that it's sort of big enough to be non-trivial and informative. You need higher level computer programming in order to process this data set, even if it is a relatively simple example. And as part of this, some of the data regarding the regional affiliation of the survey respondents is missing, and the data corresponding to these missing regions needs to be deleted. Now the easiest way of processing this data in R is to copy the data into Notepad, read the data into R using the command read.table. So that's similar to what you've seen before, and then use the command line in R to organize the data as required. Now, precisely the reason this is important is you've got a messy data example and you need the higher level programming to get the thing to process the data how you wish. If you just had to use Excel in the menus, I would have a mental breakdown at this point. Okay, the serious point being that because this is a knotty, messy data problem, you need some higher level computer programming in order to resolve that. So the same as you've seen before then, so reading the data into R, so it's easy to save the data directly onto a USB stick to make the file path shorter. Then I think this was using my work computer, so a slightly different drive letter for the USB drive in this case, but scores just goes to read.table, apply to the file path, and just make sure here that you get the correct letter for your USB drive. This might not be G on your computer, so you might need to change this number if you're doing this. So this is a serious practical data set. So you could enter it in the command line in theory, but you'll be there all day. So the easiest way to do this properly is to read in the .text file. And then the next thing to do is just read in the variables one by one. So rating goes to the first column of this data set, goes to the second column of this data set, the region goes to the third column of this data set, and the region missing goes to the fourth column of this data set. Note here as well, we've called it here, scores goes to the read.table of the .text file. So here we must have the name scores going down the columns 1, 2, 3, 4 to match the thing that we're assigning to this red table. In terms of processing the data in R then, so the easiest way to do it is to use this fourth column which indicates if the region is missing. So the idea is that this fourth column region missing gives you a value of 1 if the region is missing and 0 otherwise. So using the vectorized nature of R, what this is doing is saving the ratings values for precisely when you've got the regional data, and the same rhyme and rhythm and reason below. So the second line of our code here is to precisely those cases where you have the regional data available, and then the region command and the region variable rather here, this is again precisely restricting the region variable to those cases where you've actually got the regional data. And it just turns out that if you have this column noughts and ones in the fourth column, the region missing variable, this is the easiest way to organize the data set in this case. Now it's very simple what you're doing here, but it's a lot better than alternatives such as using Microsoft Excel. Okay, so a serious data example which needs serious software, and then you need to tell R to put the data in the right form. So the data for product and regional labels rather than numerical measurements, you need to tell R this, and in R the command to do this is factor. So this is what these final two commands in R are doing at the bottom. As this is a non-trivial problem, it's worthwhile to look at the regional data just to see if you might have made a mistake. So again, in R, the command to do this is summary. So if you just say here, summary of region, this gives you the labels and then the counts in each case. Okay, so this is in some sense completely trivial, but I think this is really relating to an important softer skill here. Okay, just checking at each stage that you've not made a mistake. So I suppose this is inevitably an aspect of econometric and financial analysis when you've got a non-trivial data set, as in this case, but I think this will also match important softer skills for accounting and finance, where the name of the game is attention to detail and just checking all the time that you haven't made an obvious mistake. Okay, and the cross-check here is just to make sure that if you summarize this variable once it's been expressed as a factor, what you get is a list of the labels and a count of how many times each of those labels occurs. So there's no obvious indication from this point that we've made a mistake. It's possible that if you did this simple step, you might see that you've made a mistake somewhere, and this need for continual checking and cross-checking is really important for econometrics and for finance and accounting more generally.